But first off, I'd like to do a little reminiscing back to when I was in elementary school, when the world was young. And I went to Trowbridge Street Elementary School in Milwaukee, Wisconsin. It was a brick 3-story elementary school, very old by the time I got there. It's still operating, by the way, which is really kind of neat. We had an external spiral fire escape outside, and our classrooms had very high ceilings and beautiful Vermont slate chalkboards, but not a lot of other resources. I mean, the books were there, the pull-down charts, but the thing that was probably the most exciting to us was the world globe. And it was a globe, well, not quite like this one, but sort of. This one doesn't have the color on it, so it's a right-on globe. But it was a world globe, and we got to play with it occasionally. So what we would do, of course, is get up there and spin it as fast as we could, and then we'd jam our fingers on it, get them caught in the little thing here. But we'd try to stop it on somewhere, and then we'd say, oh, that's a place I promised to visit someday. Most often we ended up in the Pacific Ocean, but that's the way the Earth is. But it was a good way to learn about geography. We had a good time doing that. Occasionally even we went to the encyclopedia and looked up some of these countries. So we were learning geography by playing like that. Well, the inevitable question was then asked of our teacher. I mean, something's wrong here. It's supposed to be like this. We try to adjust it and it wouldn't go. Teacher, why is the world tilted? And our teacher would tell us, well, that's the way it is. I mean, the Earth is inclined at 23.5 degrees, and it goes around the sun that way. And then comes the dreaded second question, but why? And the problem was that really people didn't know exactly why. It was sort of, that's the way it is. Well, when I went to college and started studying earth science, in particular, astronomy and geology, oceanology and meteorology, one of the things I began to realize is the implication of this inclination here. This is not something that's trivial. Actually, it has a profound influence on our lives. It's not just a fun fact about the Earth that it's tilted. It really has a profound influence. It influences what you wear every day, the foods that you eat, where you live, human migration and animal migration patterns, the cost of your energy for your home. Just one thing after another. Even the world geopolitical situation where you get the haves and the have-nots, it's all related to 23.5 degrees. It's an amazing number and what it does for us. So I'd like to share that with you today and explain some of these things. So we can have the lights off now. And I'm going to stand over here, and let's hope it's still working. And we can get the backlight too, and then it'll make it even prettier. So the presentation is 23.5 degrees. That's our topic for today. All right. First off, we do need to do a little bit of background in this, make sure that we've got all the information that we need to understand what's going on here. And my idea is to give you enough that you could explain to kids and also to be able to use it in your teaching so that you have all the pieces to this rather complex and interesting puzzle. Well, the background, some of the background I'll give you will be very, very fundamental, and some of it may cause you a little bit of problem. I don't know. We'll see if you catch all of it here, but most of it's really quite simple. For example, Earth is the third planet from the sun. Background. Earth orbits or revolves around the sun every 365.25 days. And that quarter day, of course, has to do with leap year every 4 years to get the extra day and all that. The sun's light falls on the side of Earth facing the sun. Another really simple thing. And the side facing away from the sun is in darkness. So you got a day-night. Basic concepts. Now they're going to start getting a little bit more complicated. The sun's rays are virtually parallel when they reach the Earth. Think about that for a moment. And if the sun is, the trouble is, kids often think the sun is a lot closer than it really is. And it is so far away that when those rays get to us, they're virtually parallel. You wouldn't be able to measure the difference between parallel and slightly less than parallel. And it's so close to parallel. And this has some implications in terms of, like, for example, if you want to figure out the circumference of the Earth, there's a method called the Eratosthenes method, using arcs and so forth, but parallel rays of the sun. And Eratosthenes, a long, long time ago, came within a fairly accurate answer for Earth's circumference, just using sunlight angles. So, I mean, that's an important thing right there. But here's another one. Earth rotates, causing the sun to appear to move across the sky, creating day and night cycles. Michael talked about that a few moments ago. And then the length of Earth's day is 24 hours due to its rotation and revolution around the sun. Now you might say, well, rotation, sure. I mean, yeah, but what about the revolution around the sun? That's not always known by people, but it really is important too. Have you heard about that before, that there's two things going on here? I try to explain that with the kids try to show them like a little demonstration. If you hit the light there, It's really kind of simple, actually. If you say that the sun is right there and I'm Earth, and I'm going to have my arm out like this, I'm going to do a turn, and it goes west to east, so I'll go like this. And when I am back in exactly the same place, that's 24 hours, okay? Well, that's the idea. That's one complete rotation of Earth. So I got back here like that. However, if our sun's right in the middle there, I'm also rotating. I'm revolving around the sun. So if I do this, now the trick is not to fall over your purse there. I'm going to make it bigger than I would for one day, which is a little bit. So I'm going to make it bigger, like several days. But here we go. I'm going to be moving at the same time. And now I'm pointing exactly at the direction I was before, except the sun is now there. It takes a little bit more rotation to get back to the 24 hours. So the actual period, the rotational period, is really 23 hours, 56 minutes. And you base that on stars. You look at the distant stars, 23 hours, 56 minutes, that star will be in the same place again. You got to rotate another 4 minutes to be able to get the Earth, the sun, you're pointing at the sun. Okay, the lights again. Our light people are really important parts of this presentation. Okay. Sun's light and heat energy and Earth's movements create seasons, climates, and weather. That's the direction we're going today. How does that all work, and how can you explain it to the kids? All right. Solar system concepts. Here's where we go astray. This causes a lot of problems. This is a really nice picture. I like this one a lot. And it's actually quite up to date because it has Ceres, the asteroid there. It's got Pluto and Charon listed, and then 203 UB 313, which is another distant thing. The problem with this is that it really gives everybody the wrong idea. First off, how many times have you seen all the planets lined up in a beautiful, right? Okay, gang, get together, straight line, come on. Hey, you and the sun, that doesn't happen. I mean, sometimes you get a few that are kind of in line because you can see them close to each other in the sky. All right. But that never happens this way. So that's one thing. And it sure looks like Mercury is really close to the sun. That's why it's cooked. And Pluto's way out there. It's why it's frigid and all those kind of things. It's just gives you the wrong idea. So let's take another conception. These are things you find in books and on websites too. Now that's another good one. Now we actually get the paths of the orbits here and all that. It even shows a little bit down here how Pluto intersects with the orbit of Neptune. Nice. But again, it's just the wrong scale. Now you have artistic people making these charts, and they look like this. And this is like a family portrait. It's like school photo day, the whole class, We get them all together, and, for this reason, these charts right here is why solar system models are usually banned in science fairs. Every science fair I've been to, you're not allowed to do a solar system model. You know what the deal is. The kid gets a cardboard box, paints it black inside, hangs a bunch of styrofoam balls, and the solar system. Doesn't work. It's all, the problem is, if you try to make models that the sizes of the objects are in scale to each other, okay, but then you can't do the distance. The distances are incredibly long. You just really can't do both at one time. So you don't really make a true model. All you do is make styrofoam balls to look sort of like the planets. Well, let's take a look at some models here. And we're actually going to do some actual models in the room here in a moment. I'll show you one on the screen here. If we say there's the sun, and Earth would be way over there. I'm going to cross the screen here for this and show you. That dot is way too big. If I were to make this dot properly to scale on this model, this dot would be microscopic. But the distance, based on the sun being that size, and to here, that's correct on the model. But this has to be microscopic, and you wouldn't see it. All right. Notice down here a little red line right there. We talk to kids about the seasons, and sometimes they'll say, well, the Earth is closer to the sun in the summertime and farther away in the winter. That's a very common misconception, and I'll tell you that misconception goes through all of society. There's a wonderful movie called Private Universe where recent Harvard graduates are being asked while they're wearing their caps and gowns to explain the seasons. And they come up with all kinds of crazy ideas, none of them that actually fit. None of them are on target. They're all incorrect. Well, that spot right there, from there to there, is the orbital variation at scale of Earth. It does have an orbit that's slightly elliptical, and it gets a little farther and a little closer at different times of the year. The difference between the two is about 1 million miles from the close point to the far point. So In the northern hemisphere, when we're right over here, that's wintertime. And in the northern hemisphere, when it's summer, it's right over there. It's about 1 million miles farther away. Okay, that's a good teaching event there, because you can say, hey, look, it's not the way you think it is. It's reversed. All right. Okay. I'm going to work with you and make a model. But first off, let's do the facts. Sun's diameter, you see it there, the sun's circumference, the distance to Earth, the mean difference, and then we got a crazy little number here called circumference to distance ratio. This is the number I manufactured. You won't find this in planetary charts. It's a really cool number because of what you can do with it. What you do is you take the circumference of the sun and divide it into its mean distance to Earth. And it turns out it's 34 times the circumference. That's what we work with. So we can have the lights back on. I'll show you just exactly how that works. Went to Toys R Us and I bought this ball here. It's about 8 inches in diameter. It's just whatever, doesn't matter what size ball it was. I just picked out this one. That's going to be great. And I want to make a model using the sun and an Earth model, make them to scale and put them away from each other at the distance that would be scale. Now, first off, I got to figure out what the size of Earth is. So a little stick right here with a bead on top of it. Actually, this bead is a little too large. It's 1 millimeter too large in diameter. So that's Earth and sun. And fun thing to do with the kids, they say, okay, now tell me, where should we put these? How far apart should they be? Everybody agree? No, yes, no. And kids will have you move it closer or farther away, you know, and so forth. Is that your final answer and all that? Okay, how do you actually figure it out? Well, that's where the fun part comes in here. I'm going to use a string and use our circumference to distance ratio. And I found out it's a little bit tricky to do this. You can have the kids do it, and you know, by the end of the day they should have it done. So I've practiced by kind of doing it this way here. So I go around one time, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, I may have missed one there, 28, 29, 30, 31, 32, 33, 34. Got it. And I'm going to make a knot right here so we don't lose this spot. Okay. Now I need the help of some volunteers. Okay, and the 2 of you, okay. And the rest of you, you're also volunteering to go outside into the hall. We're going to be out there. As you can see in this demonstration, we need a rather long haul to make it work. One of the teachers in this case takes the sun globe, and the other one takes the model of Earth, and they start walking apart from each other, using the string as our reference point. So it stretches out further and further. With the 8-inch diameter sun that we have, and our Earth being about a 1/10 of an inch in diameter, the two of them to be at scale have to be approximately 75 feet apart. And if you're standing at the sun looking out towards Earth, it's almost invisible in that hallway. It is so tiny and so far away. Okay, now one of the neat things about this number, this 1 to 34, is that it doesn't matter how big this is. If you used an orange, it would still be 34 times around, and the model would still be to scale. Now, Earth would have to be smaller, of course, but you start with this as your base thing, and then you build your model from this particular size. So if that one there, larger, still will be 34 times around. So that's the way that works. The only thing is you've got to adjust the diameter of Earth. Okay, now that's one model, but let's go a little bit further with this to get another idea why it's difficult to do science fair projects of solar systems. I mean, you can't get that into a box. If you made it fit a box, then the sun would even be microscopic at that scale. All right, there's another couple of numbers here. Earth diameter and diameter ratio to the diameter of the sun. So this diameter divided into that diameter gives us a ratio of 110. And here's what that looks like. There's Earth and the sun at scale. (110) to cross the sun. So that's what it would really look like if you made a necklace of Earth's, it would take 110 just across the side that you can see. But there's a lot more to this across the disk there. If you go around like it's three-dimensional, well, then it would take 346 Earths to circle the sun. So I can make a choker-type necklace. All right, let's do a model of that. That's kind of fun to do. Light again, please.
Just to do the circumference, not how many Earths can actually fit in.
Yeah. The first now, the number that actually fits inside would be about 1 million. Okay. Would you like to be the Earth Girl? Come on, up here. This is Earth Girl. Please turn around there. And working with little kids in particular, I'll get out various sizes of globes and show the kids, what's this? And they'll say it's Earth. And I say, no, that's not Earth. This is Earth. That's a model. And you try different sizes. Eventually you get the idea that when you make a model, you can make it any size you want. So then I say to them, this is a model of Earth. Now I used an orange one so you can see it better. If we had a blue, you would kind of lose it. So, but it's orange. So I'm going to put it around your head there. Going to let it hang down. So that's your Earth necklace. And if Earth were that size, and I made a necklace to fit the sun, every bead the same size as Earth, okay, I would need 346 beads to make a necklace that would go exactly around the sun. And this is your dollar store special, you know. You like to turn around? You can see it yourself that way. See how big that is compared. So that's a good representation of the size again. And it shows how difficult it is to put all these together in a box. Okay, if you can take that off, please. Thank you. All right, thank you. And I thank also our sun and Earth out in the hall. They did a good job there too. And thank you for coiling up the string properly and safely. Okay, back to the lights. Now we're going to get down to what we're aiming for here, and that is a planet for all seasons. Where do the seasons come from and how do you explain it? And all those kind of things like that. Back to this implication of the 23.5 degrees and why. We're even going to get to that answer that I couldn't get from my teacher because we didn't know it back then. The why will come along as well. First off, some more background, just to make sure we understand what 23.5 degrees means. The dashed line represents the planes of Earth's orbit. The astronomy name is the celestial equator. If you could watch the sun every day, you know, like they do in that planetarium program on the computer that you were looking at a little while ago, if you could watch the sun every day with the sky, you know, dark enough so you could see the background stars too, you could draw a path. Today it's here, tomorrow it's there. You could draw a line showing every place where the sun is located for a whole year. That line is called the ecliptic. That's all that is. So that's what you got right there. And Earth, when it spins, as it's going around the sun, the axis, the axial tilt, is 23.5 degrees. It keeps that the entire time. So that's what we're talking about. It's tilted to the plane of the ecliptic, to the plane of our orbit, in other words. So what does that mean? Well, let's show that here with this diagram. And here's where things get a little complicated and you can have fun with. We call this parallelism, and we'll do a demonstration on that in a bit, but not just now. Parallelism. Northern hemisphere. If you look at the arrangements here of the body, the planet and so forth at different positions, well, that would be called summer. The North Pole axis is kind of pointing towards the sun, sort of in that general direction. And the high latitudes, the sun's high in the sky and so forth. Then we have fall, then we got winter, and then we got spring. Now here's where the fun part comes in. There are people in Australia that would be rather offended by this diagram and say, hey Mac, we got seasons too, you know. Southern hemisphere. At the same time it's summer up here, it's winter down there. Fall, spring, winter, summer, and spring, fall. The seasons are reversed. Now back to that business about, well, the sun is closer to Earth, or Earth is closer to the sun in summertime. If you're an Australian teacher, you have to say yes, but. Because in fact, for Australian kids, the sun is in fact closer in the summer than in winter. It's just the reverse from us. So that's a little bit confusing. If you decide to ever take a teaching job down there, remember everything's upside down. Okay. That's right there. And so the thing is, seasons are not caused by varying distances to the sun. That's the big message from this particular diagram. So let's do a tale of two sunbeams. There's our Earth, and make the atmosphere. And I want to point out to you the caution, the thickness of the atmosphere is greatly exaggerated. Okay. What did I just do here? Did I hit the button? Okay. Hold on. Let me. I think I hit the button too fast. Let's try that again. All right. Okay. Now. Huh. Oh, there we go. I got confused. Sunlight. We got two beams coming from the sun, and they're parallel. And then the sunlight. When it's summertime in the northern hemisphere, the sunlight's at a very high angle. So if you look at that angle right there, the red line, this red line right here represents the horizon that you would see if you were standing at that point right there. And the sun is at a very high angle.
Remember we saw that in Solarium where it's up, 70 degrees or 70 degrees, you could see that angle there.
Then if you're down here, down under, at the same time, there's your horizon, so your head is kind of pointed this way. The sun is very low in the sky. So you have a high angle at one place, at the same time you have a low angle at another. Here's the important point. High angle sunlight concentrates light. Low angle spreads it out. Now we can go to that old classic demonstration with a flashlight. I'll just get my light on here. And you can show this to kids like, well, all right, look how bright that is. And if you have a low angle, keeping the distance the same, you see how that it's getting dimmer and dimmer. So you have less light being concentrated at the low angle, and it's really concentrated at the high angle. That's what's going on here. Now we have another factor too, and that's the distance. When the sunlight comes through the atmosphere, the angle is very high. It has a relatively short distance. And of course, we're really, when you get a model of the Earth and you try to make the atmosphere visible, you really have to expand it, make it big in the model. But in fact, if you had an Earth the size of, say, a tennis ball, the atmosphere would only be the fuzz on the outside. That's all it would be. So this is really a great distance shown here. But the point is still made, though. Right there, a great distance, a short distance rather, and then a greater distance down here at the lower angle. See how when I move them together, you can see there's quite a distance difference between those two. And the big point is, shorter distance means more heat and light reaches Earth's surface because the atmosphere does filter energy. It's not as bright when you have a greater distance to travel through. Think about that when it's sunset, when the sky is reddish and so forth, and it has a great distance to penetrate through the atmosphere. It really filters away the energy from the sun, the light and heat energy. And there's more to it. The hours of daylight in summertime, and of course everything's reversed in winter, but in summertime you've got a lot of daylight and less hours of night. Down here though, look at how short that arc is compared to how long that one is. More nighttime, less daytime. So you have less time to build up the heat from the sun. So you take all of these and put them together. Again, the main point, more hours of daylight, more heating. You take all these together to sum them up. In summer, sunlight is more direct. The sun is higher in the sky at noon. In winter, sunlight is less direct. The sun is lower in the sky at noon. In summer, sunlight has a shorter trip through Earth's atmosphere. In winter, sunlight has a longer trip through Earth's atmosphere, and I say I misspelled atmosphere. And in summer, there are more hours of daylight. Okay, that's how things. Oh, finally, in winter, there are fewer hours of daylight. So you put all those together. Can we have the lights back on, please? Okay. Time for another demonstration. And this one's kind of fun to do. Let's see. Okay, it involves one of these things, these pull sticks. This is a great invention. It's called a graviton, or gravitron, I don't know, one of those two. It is a gyroscope. To understand about inclination, you need a gyroscope. When kids can feel a gyroscope and feel the forces involved, it's really a neat thing to do. This particular kind of gyroscope is nice because it's kind of enclosed. You use one of these pull sticks with the teeth on it, and as a result, you don't have to worry about like the string getting caught around the axle. If you ever play with the old gyroscope, you pull it and then suddenly it stops, or the string breaks or they got stuck. That doesn't happen with this kind right here. Okay. What I'll have you do is you get it spinning like that. If you go like this, you can do that no problem at all. Okay? Pretend the sun's right here and you're going around the sun. Well, the angle really is 23.5 degrees. So tilt it like that and go like this. You'll find out once you've got it there, it's easy to do. But then, what I'd like you to try is this. Going around the sun, tip it like different angles. See if you can do that. You will find an interesting feel to the gyroscope when you try that. When you try to change the angle when it goes around the sun. So here's the deal. You just simply go. I got it like that. Then I try it like this. And you'll see what I'm talking about. And it's good for kids to do too. And by the way, these gravitons have flown on the space shuttle. When I worked at NASA, we flew several of these in a movie called Toys in Space 2. I worked on that one. You'll see these exact things in them. This is a gyroscope. And a gyroscope is an interesting toy, but it's also used in a lot of applications. Ocean-going ships, especially the ones that have tourists on there, they'll put gyroscopes inside the ship to dampen the rolling motion. It really resists that. Riding a bicycle, you got your wheels spinning. It helps you to stay up. You don't fall off the bicycle once you get going. Well, what's happening is if you have a heavy flywheel inside and you get to spin like crazy, what you're doing is creating a great deal of inertia. Newton's first law, inertia. You get that spinning. If you want to change direction, you have to add an unbalanced force. Go to Newton's first law of motion. Objects in motion stay in motion unless acted upon by an unbalanced force. To change the direction, you have to add a force to it. That's why it wants to keep the same inclination. Now, I know you're looking at the gyroscope when it's on that little platform and you're thinking, well, now it's changing direction real nicely. Well, think about this. You put one end on the little stand and the other end is not supported, you are actually putting an unbalanced force on one end because gravity is trying to pull it down and that's trying to change it, and the gyroscope fights it and it goes through a precession motion. All right, that kind of explains, I think, how this works. Now, if you want to get to a bigger way of doing this, you can also get like a tricycle wheel and get one of those that's not connected pedals, but a good spinning wheel, add some weight to it. You don't have to buy these really expensive ones in the science catalogs. And it's great. You can put a kid on a stool and have them do that kind of stuff too, and the stool actually spins when they add a force to it. It's really wonderful to do. Well, that kind of gives you an idea of this inclination. That's why we have it. Earth has been spinning like this. It has a huge amount of inertia. Think of the mass of the Earth. It has a huge amount of inertia, and it doesn't want to change its direction. It would take a lot of force to change the direction. I guess it's time to go into that thing about why Earth is inclined.
Yes.
Okay, it's time. All right, here's the idea, and it happened so long ago that you can argue with me about it, but you weren't there and I wasn't either, so I'm winning the argument. It happened billions of years ago. There's been some interest in trying to explain where the moon came from, and I think the tilt of Earth axis and the moon creation took place about the same time. It is believed that at one point, when Earth was still pretty much of a molten ball, maybe had a little solid surface, but not much, it was struck by a Mars-sized planet. The iron cores of the two bodies merged together to form a really big iron core for the planet Earth. At the same time, a lot of melting, extreme amount of heat and melting and so forth, a big amount of it splashed off, went into orbit around Earth, and eventually coalesced to become the moon. Well, the idea is that when this thing hit it just the right direction to cause Earth's axis to tilt. It was a huge force and it pushed it over. That's the idea there. There are other planets that are tilted over. If you read about the planet Uranus, all the books will tell you it is thought that Uranus was struck by a body like that too, and was pushed over on its side actually. So that would be an answer that nobody can verify and prove, but it looks pretty good and it's the only reasonable one we can think of. Yes?
If it's a gas planet, how are they able to have that kind of impact?
Well, when these things hit, the force is just terrific, and Uranus is not totally gas. It's also rock inside. And yeah, the point, yeah, it would still hit, and it'd be enough to push it, yeah. I mean, you can't just run through the air at infinite speeds. You have a lot of drag. So an object would cause a lot of force and so forth to being transferred from one to another. If you remember a few years ago, Jupiter got struck by comets. And all we saw was the impact. Well, actually, we saw it after it happened because it was just on the far side of Jupiter. But when those comets hit, the fragments hit, they produced tremendous explosions because at the high speeds they were hitting, and a tremendous amount of force was generated by that, and big black clouds and just all kinds of things happening. But that happened a few years ago. In the 90s, I think, that took place. You can check on that. But it didn't alter Jupiter because the comet wasn't big enough to do that. Okay, let's have the lights again, please. We're going to start wrapping this up a little bit here with the big question like, okay, what does it mean to me? Here's a classic diagram. I just wanted to show this to you because here's what this is all about. Let's say the sun's rays are coming down to Earth. And it heats up, especially the urban areas, the agricultural areas. The water doesn't heat up nearly as fast. And we end up causing air currents, rising air currents, and the air cools off, it falls back down and so forth. What we're doing is we're creating wind. This is a summertime condition. In the wintertime, you just reverse it. Then you have the cold air falling over the city, but wind is produced. And what this amounts to simply is that when you have changes in the sun angle and so forth, we end up producing weather patterns that alter constantly. And this determines our weather, it determines our climate, and our climate really is nothing more than just the sum total of weather for the year. Like you take all your averages and you figure out what your average temperature is. That's the climate thing. So these seasonal changes that are produced by Earth's inclination and the position to the sun lead to eventually our day-to-day weather and all the factors that affect us because of that day-to-day weather. Well, the sun is our heat engine and it drives the weather. Now we're going to just go with a couple of challenge questions for the fun of it. What would happen if we had Earth with an axial tilt of 0 degrees? Would we have no seasons? What do you think it would be like? Let's say that you lived at the equator.
It'd be hot all the time.
Be hot all the time? You lived at the North Pole or the South Pole? Cold. Every day would be pretty much like every other day. Yeah. And how much daylight would you get at the North Pole?
0. Well, yeah.
How much at the South Pole? How much at the equator?
A lot.
Remember now, we're up and down.
Every day would be 12 hours sunlight, 12 hours night.
Every day, 12 hours sunlight, 12 hours night. And if you're at the pole, you'd see the sun at the horizon, just about. I mean, it would be just below the horizon maybe, but you would see it there. The sun would just kind of go around you every day. In the case here, I mean, at the equator, 12 hours and 12 hours. Everybody gets 12 and 12. All right, let's try a different example. What would happen if our axial tilt were 90 degrees?
South Pole or North Pole will get endless sunlight and vice versa.
Now we're going around the sun, remember. Would the weather change and the climate and seasons? Would we have seasons? Okay. Yeah, well, yeah, really, we would have seasons, except our seasons would last half a year. For half the year, the South Pole is kind of pointed sort of at the sun, and then for half a year, the North Pole is at the sun. Well, here's a chart showing axial tilt of all the planets. Mercury is virtually 0. And Venus, 177.4. That's odd. Earth, 23.5. Mars is 25.2. That's pretty good. Jupiter is still almost vertical. Saturn and look at Uranus, 97.8. Let's have the lights on again. Just to make sure you understand this business about angles. Pretend that this is the axis of Earth. And we're starting at 0 degrees right here. If you got 90 degrees, or actually 97 degrees for the planet Uranus, you go down like this, that's 90, and a few more is 97. And with Venus, it's 90, almost upside down, not quite. That would be Venus. Now the implication of that is that Venus rotates a different direction from the other planets. Okay. Let's say we're rotating like this. Okay, now I'm going counterclockwise at the moment. Okay, so the planet's going counterclockwise. Let's tip the thing upside down. I'm going to try to keep this going here. See, now I'm going clockwise. So that's when, if kids say, hey, Venus goes clockwise, here's why. So it just flips it upside down. Well, we pretty much covered everything I wanted to share with you.